and it's definitely much cleaner and has more sort of comments about what's going on in the code than the original did. So we have the original code, and I'm listing the sort of citation for all these codes. And this led to the open source sort of cleaned and optimized version that was given to the Einstein toolkit as IllinoisGRMHD. But this only includes a specific kind of nuclear equation of state, the hybrid equation of state. And people started wanting to have a more advanced way of modeling the nuclear matter in the code. And the one way to do that is something called tabulated equation of state. I'm not really going to go into what different kinds of EOSs mean or are, just take it on faith at this point. There's a tabulated equation of state that's generally better in the sense of being more accurate and having more accurate simulations. And so multiple groups wanted to do this. And one of the sort of downsides one can see of an open source code is that everyone decided to do it themselves. And so everyone spawned off their own IllinoisGRMHD variant that now are sort of mutually exclusive. There's no real clean way to combine these efforts. And because of that, instead of having a sort of collaborative open source code, we now have fractured into smaller sub-communities, which isn't really what one hopes for when one makes an open source code. So we sort of saw this and said, well, that's not great. I'll just briefly say, so they all added tabulated equation of state. This one also added neutrino leakage and some higher order methods. And then the one that our group made does tabulated equation of state, and then also neutrino leakage, which is sort of the simplest radiation transport scheme for neutrinos. So our group decided to make a code library from our IllinoisGRMHD so that we could sort of try to avoid this happening again, at least in our branch of the IllinoisGRMHD line. And that's GRHayl. So this is the general relativistic hydrodynamics library. And so we've refactored IllinoisGRMHD into modular components. And all of the functions inside the library are either pointwise or explicit stencil-wise, meaning that it doesn't have to reference grid functions or make any infrastructure-specific calls, which means we can use this library across multiple infrastructures, not just the Einstein toolkit. And so this is also sort of the future of IllinoisGRMHD, or at least the IllinoisGRMHD that's in the official toolkit release. And it includes better separation of the code into independent modules. Before it was all sort of mixed together and hard to figure out what was doing which piece of the whole GRMHD sort of algorithm pieces. And there's much better documentation. Most of the GRayl functions, hopefully they all, have individual pages on the GitHub wiki of the library saying what are the inputs, what are the outputs, what does this function do? You know, the sort of documentation one would hope for a library. And of course, now GRayl isn't bound to the Einstein toolkit, so people can freely develop an IllinoisGRMHD-like code in whatever infrastructure they want. I'm not going to really focus on that too much since this is obviously about the Einstein toolkit more than other infrastructures. But if you do have an infrastructure that you use outside of the toolkit, you can also consider GRayl to develop a GRMHD code there. And also, one thing about code that is often sort of ignored in a lot of science codes is we should try to make tests to validate that the code continues to work in the future and not just assume or hope that since we tested it once, it will always work. And so GRayl has automated continuous integration or CI testing using GitHub Actions. And basically for all the code that comes from old IllinoisGRMHD, we have a way of validating that the output that we produce in the current version of GRayl matches the old IllinoisGRMHD. And for things that are completely new in GRayl, we have tests that basically validate against a trusted version of the GRayl code. And these unit tests covered 97% of the code base, which is a very high percentage. If you're familiar with unit testing, that's basically the whole thing. The remaining parts are like error branches or small things that are like where we would have to really go in and get individual tests to get another 2 lines of the code or something like that. So that's a very high percentage to cover. So this is sort of this is the old Illinois GRMHD is this tangled octopus, right? And the goal of GRHayl is to sort of take this confusing mess and make it clean and separate out what all the different pieces are, right? So how we do that is if you have your core code, right? You have cactus and design toolkit, and you make a thorn, and inside of it you have a scheduled function with a loop. And inside of that loop, you pass the grid data into these pointwise or stencil-wise GRHayl functions. You just pass the local data. You're not passing anything about grid functions. And then that goes out to the specific function you want, which are all cleanly separated into various sort of subcategories. And then the function you call goes and does whatever it does, and then comes back, gives you the data, which you can then put into a grid function or do whatever you want to do with it after that point. And so that's sort of the general idea. And if you, let's say you wanted to make a pure hydrodynamic code, obviously you don't need the induction equation part, so you can just ignore that that's there and not use it. If you already have a code, but you wanted to use some of the conservative derivative recovery routines that GRHayl has, you could use those and not replace the rest of the code, right? The idea is that it's a code library. You can use the pieces you want. And so long as you give GRHayl what it expects, then you can use the pieces that you like without needing to use everything else. So, you know, that's in Cactus Carpet with GRHayl. This gives us IllinoisGRMHD. But let's say there's already another code which uses the Black Holes at Home infrastructure and adds GRHayl to it. And we have the Groovy code, which Terence Pierre-Jacques is the lead developer of. So, you know, there's already examples of GRHayl being used in multiple infrastructures. There's also work in the Manga code to use pieces of GRHayl. And, you know, the idea is that all the stuff in GRHayl we can just keep reusing, even as infrastructures change. And as new algorithms come out, we can replace the parts that we need in our implementation by just adding new library functions to GRHayl and using them where we need them. Instead of having to tear out the guts of IllinoisGRMHD every time we get a new carpet X or carpet Z or, you know, whatever comes next, that we have minimized the amount of work we have to do to keep up to date, basically. So I'm just going to sort of go through those modules I listed earlier, just to sort of say what's in them. Now, Atmosphere right now is pretty unexciting, I'd say. It only has the constant atmosphere prescription. There's some people at RIT that are interested in adding radial fall-off prescription as well. And if people have other atmosphere prescriptions they're interested in, of course, this is where they'll live. But for now, there's just the one. Now, neutrinos, which I aim to eventually rename radiation, provides the core algorithms for neutrino leakage. There's other schemes that people are already planning to work on that they will eventually, hopefully, add to GRHayl. And there's a M1 closure scheme that's planned, as well as photon transport schemes. And you know, as they work on these, they're already using GRHayl, and the goal is for them to sort of develop these and then figure out what pieces can be separated from the infrastructure and give back to GRHayl, right? And that's sort of the idea of making this library, is that people can work on what they want without changing things that make it incompatible with other people. And the flux source module, of course, provides functions for computing the characteristic speeds, which are needed both for the fluxes and for the induction equation. And then also the source terms and fluxes for the conservative variables for computing the right-hand sides. And this includes both entropy and the electron fraction, which is for tabulated equation of state. So depending on which equation of state you're using and whether or not you're involving entropy, you're going to want slightly different functions from GRHayl, and we have the different variants provided for whatever you want to use there. Now, for the equation of state module, the EOS module, we have simple gamma law, hybrid piecewise polyprobe, and tabulated EOS. And we have sort of abstracted away the function calls so that it's easier to swap them out. So let's say there's a specific thing you want to try out maybe you have an interpolator that's different that you think will be faster, and you want to swap out that piece of the tabulated equation of state, or you want to change other pieces of this module. You can do that. Now, the reason that this is sort of more complicated than the other modules is because all of them implicitly depend on the equation of state. So we have to do this sort of extra layer to sort of allow you to swap out the functions without having to dig into the other pieces of GRHayl. But the idea is, you can play around with, what's your question?
This might be too much detail, so if you have different equations of state, I can see that you can easily support, say, both gamma law and the hyperspecified potential function of Cupp, because you take the same set of independent variables. If you add a tabulated equation of state, and then have to do calculations position, you can extra variables.
Right.
Way of doing this without lots of if that's.
Okay, so the question that Roland asked was, since simple gamma law and hybrid piecewise polytrope are essentially the same thing, just one's a special case. The tabulated has extra variables, and it's quite different. So, in terms of the core tabulated functions, of course, if you're doing something that needs to call the table interpolator, then you're doing a tabulated code. There's not really a swap out for that. But if you're looking at, say, a conservative primitive routine, there are some routines that are purely for hybrid and some purely for tabulated, sure. But the actual argument lists for those don't change because there's a primitive struct. And that struct contains a double for YE for the electron fraction. But if you're doing hybrid, of course, the electron fraction just isn't in that case. But yeah, some of the functions don't have equivalence, but for the ones which they do, of course, they can be swapped out. But the goal here is sort of, let's say you wanted to test out pieces of like Jonah's singularity EOS and see if his interpolators are better than ours. Then you could switch those out and make sort of an interface for that without having to go in and change every single part that uses the equation of state function. Yeah.
Right. Hold on. So basically, that means that GRHayl decides physics that's portable, that's essentially coded in the that you have. If I want to say, I don't want equation of state, these variables I have to change to lower levels of GRHayl.
Right, so you would have to change, yeah, so I mean, depending on what exactly you would want to add, you would probably have to change things. How much kind of depends, right? I mean, most likely you're going to need completely new conservative primitive routines, so you're not going to touch the old primitive routines, right? You're going to have a new one that expects extra things, and without seeing an example, I don't know that I can give a good statement of what all you'd have to change, but I mean, potentially, you might have to add in primitive variables, but right now, the primitives, at worst, you add YE and T, for example, and entropy. So there might be 3 more, but this is all pointwise, so it's not like you're really wasting a lot of memory by having those in there. If you're going to add 100 new primitive variables to the primitive struct, I don't think I'm going to really be on board with that. But if it's 1 or 2, then, that's fine, right? It's sort of, because of the pointwise, it's not like you're adding a whole grid function or something. So it's not as big of a deal to have these floating around inside the struct but not being used, at least in my opinion. But yeah, it really depends on how extreme the changes are on what you would need to do. All right. Any other questions? Okay. And then, so the conduct module, which we just sort of mentioned, provides several options for both the gamma law hybrid and tabulated equation of state. We also provided an automated backup routine, which lets you set up to 3 backups. So if your primary conduct fails to find a good primitive values, then it will try backups until it succeeds, or it returns that they all failed. Which hopefully is not the case. Now, if you want to do if you for some reason want to have more than 3 backups, or you want to have some more specialized selection method, you can of course do that yourself. We just provide a simple sort of, if failed, try next. If that failed, try the next one. But of course, you can construct whatever sort of backup system you want for your code. If there's something more advanced that you want to try. And then the induction module has functions that sort of facilitate computing the right-hand sides for the vector potential and the electromagnetic scalar potential. These are all staggered variables. We assume they're staggered. If you're trying to do them not staggered, then we don't have that support right now. And part of this involves interpolators to help you get grid functions to these staggered points. And those interpolators provide also various options depending on where the metric is being kept relative to the hydro variables, because generally the hydrodynamic variables are cell-centered, and different people keep the metric components at different places. Some keep them at the cell centers, like how Carpet does. Carpet X has the hydro variables at cell centers with the metric at vertex and vertices. And we have different variants of that interpolator function, depending on how the metric is stored relative to the hydro variables. And then the reconstruction module is the last one then currently, and it just has methods for computing the face values of the cell-centered quantity. Right now, we have min-mod, MC, super B, and PPM, but it would be very easy if somebody wanted to add new ones to put those in there. It would probably take someone that had we know and just wanted to throw it in there, like at most, even with documentation, probably an hour if they if they just wanted to implement it. But those are the ones we currently have. So that's sort of the features in GRHayl. Now in the toolkit, we already included as of the ET2311 release. We have the GRHayl library in the GRHayl form, and all of the options that GRHayl has are set up and controlled through the form. So you don't have to link to an external library or do anything like that. The GRHayl source code is just directly compiled as if it were a normal form. So Thorns using GRHayl can just inherit GRHayl lib, and then the GRHayl lib.h header contains access to all of the GRHayl functions. So if you just add this to the interface.ccl, Roland doesn't like that. I can see him grimacing, but I'm just going to ignore that. And so any files that use GRHayl functions can just include this header file and they have access. Don't worry, Roland, they do all have GHL underscore at the start of them at least. So there's some likelihood that they won't click. If that makes you feel any better, I don't think it does. Good enough. And this library will work for both Carpet and Carpet X, with the important caveat that right now all the GRHayl functions are only available on the host. We haven't worked on the GPU support yet. Once we have GPU support in GRHayl, it should be a pretty simple matter of making it available in the toolkit, although, that's easy to say, but until it's done, I don't know how many people will believe me, but that's a future goal that we just haven't had time to work on yet. Now I'm going to go through thorns in the toolkit that actually use GRHayl. So IllinoisGRMHD, the 2311 release, it's still the old version, but the current release that's upcoming should include the new GRHayl-based IllinoisGRMHD. And so this, of course, the thorn has been refactored to use GRHayl lib. And these helper thorns are now deprecated because they basically contain a single function that's needed for IllinoisGRMHD to work, and only work for IllinoisGRMHD. So there's really no need to have separate thorns just to do that. So we sort of combined all these together while reworking everything. And we also combined the official release code, which only supported a sort of a simple polytropic hybrid equation of state, with the Wernick et al., which lets you have piecewise polytropes as well as tabulated equation of state. So this pulls in both the support for more advanced hybrid equation of states and tabulated equation of state. And this also lets you have more conda-prim backup options and lets you control what's happening in conda-prim more. Before it was all hard-coded, but now you can decide what conda-prim routines you want to use and in what order. And so, it basically lets you try out new methods. And let's say a new conduct frame is added to the GRHayl, then you can immediately use it with this thorn. You don't have to do anything special. It just calls the GRHayl conduct frame routine. And we also changed, so this isn't connected to GRHayl directly, but the source terms require metric derivatives, and it just takes the derivatives that you give it. So GRHayl doesn't know how you got them, but we changed it IllinoisGRMHD how it was actually computing the metric derivatives to be fourth order, and it's actually showed clearly more accurate simulations. Also, probably partially due to this and other code cleanup we've done, that the code is now really less sensitive to small changes in initial data. I'm
sorry. I'm confused. I say higher order metric derivatives that are mentioned fourth.
So
isn't fourth like fairly standard?
So IllinoisGRMHD, what it did before was it combined the flux and source stuff all in one loop. And what it did was it calculated the face values using a fourth order interpolation. And then it computed the derivative for the center using a second order derivative of the faces.
Oh.
So it's second order derivative of the face value. It was somewhat strange.
Okay.
So yeah, it was a second order derivative. So
All right.
even though it implicitly depended on the same stencil size,
Right.
because it was doing the face values, it was a second order derivative.
Okay.
So we just directly use the fourth order derivative, and it's better, which I don't think anyone's surprised about, but yeah. And also due to these code improvements and how we cleaned it up, we removed 40% of the grid functions from IllinoisGRMHD because we just don't need them anymore. So yeah, that's quite a lot of grid functions actually. I don't remember the count off the top of my head, but it's probably close to 30 or 40, I think. It's definitely more than 20. Yeah. We also provide a simplified thorn, GRHayl and GRHayl-HDX. And so GRHayl-HD provides a purely hydrodynamic version of IllinoisGRMHD. And this reduces the number of grid functions instead of 40% by 80% of the old IllinoisGRMHD. Because we can remove a large number of additional variables because we just don't have any of the magnetic variables. We don't need to store some of the reconstructed variables anymore. So we can really clean up what was going on in the thorn if it's truly a pure hydro. And then GRHayl-HDX implements the exact same thing, but for carpet X. Of course, GRHayl is only available on the host, so therefore this only runs on the host. Once the GRHayl live thorn supports GPUs, all we have to do in this thorn is change the loop macros to run on device instead of host, and then it should just work. Yeah, but basically the only thing preventing us from doing that is that the GRHayl functions aren't on the device, so if you try to do it, it won't pop. We also have a GRHayl ID and IDX, and these provide some just very simple initial data options. So we have like a 1D sound wave, shock tube, and a 5 pulsar tests. Just in case people want to use those to test their codes, we use them for testing IllinoisGRMHD and GRHayl-HD. And then we also have a constant density sphere and isotropic gas initial data setups. These last two are only for tabulated equation of state. And I know the pulsar tests are only for hybrid. I forget what these are doing in terms of, I know they work for hybrid. I forget if these two work for tabulated. We also provide the option to enforce data equilibrium on the tabulated equation of state and initial data. And this can be done to other initial data thorns as well. So let's say you set up initial data using the Moudon thorns or Fuka, but you want to enforce beta equilibrium, then you could use this thorn to do that. So long as, in the case of Moudon, of course, it uses EOS and Omni instead of GRHayl-lib, and we currently don't have the interface for GRHayl-lib to provide the EOS Omni functions in the interface. But At least for now, one can simply activate them both and make sure they have the same equation of state set up. And then you can use this to enforce it on any initial data you want. And it'll run after the initial data bin, so it's guaranteed to happen as long as it's scheduled. They should. Similarly, we can compute the entropy from the initial data. Again, this doesn't require to use this thorn to set up the actual initial data. It's a sort of runs after the initial data bin. And of course, GRHayl IDX provides the exact same features, but for ARPANEX. And again, it only runs on the host for now. Eventually, it'll run on the device, but for now it doesn't. Okay, so I mentioned earlier that the new code is sort of more consistent. So this is a BNS or binary neutron star merger after they merged, and this is the hypermassive neutron star oscillating and then collapsing. And so what we've done is we've perturbed it at the 14th significant digit, so basically round off level. And then I also just to see perturbed at the 9th significant digit, so basically a single precision error. And the old code, we see even at round off level changes to the initial data, it manages to get a whole extra oscillation at that level of perturbation, which is not ideal, I would say.
I'm sorry, what is the perturbation that you did?
I perturbed all the initial data primitives.
But you mean like you added random numbers or?
Yeah, basically the final digit, I just randomly changed something at the 14th significant digit.
Okay.
Yeah, that's how I sort of changed the round off level error. So basically the hypermassive neutron star is quite sensitive. And in IllinoisGRMHD, the old version, it was very sensitive to what you were doing to the round off basically.
But shouldn't it be the case, right? I mean, if you're randomly changing all these digits, shouldn't you get something different every time you run this if it is really sensitive to it?
I mean, probably if you run on a different machine, I mean, I would assume you're going to get a slightly different oscillation, but I don't know how many people are running the same thing, the same simulation for a production level BNS on multiple machines all the time, right? That's
But if you're randomly assigning digits, right? Each time you should assign different random digits. And each time you do the perturbation, you'll get different random digits, right?
if you choose a different seed, yeah.
Okay, you're locking down the seed.
Yeah, that's so that this and this have the same initial data, even when you perturb it. That's sort of cool.
I see.
Because if we don't set the seed, then we don't know that these are equivalent at all.
Right.
I mean, obviously, okay, I'll preface it by saying this is clearly not a statistically, I would need to run hundreds of these to tell you that for sure with 90% confidence that it's, but at least it appears the case that GRHayl does do somewhat better in being the same. Now, it's possible that GRHayl simply got lucky, but considering most of the code is basically identical, if we simply cleaned it up and pulled it out into a separate function, the things that we have changed, such as the metric derivatives or some of the kind of prim stuff that was doing lots of math and then said canceled out on both ends, if you just fixed what you were doing, that basically was probably that's just going to slightly jiggle what the number is. Once you clean up all these little things, it seems like it's not as. I mean, I could be wrong. Again, it's possible that they're the same when we just start lucky. I won't deny that possibility. But at least the few things we've seen suggest that at the very least, GRHayl is clearly much more clustered. And all of the simulations of GRHayl are close to where the old IGM would be in terms of having sort of round off level differences. I mean, this is basically right here.
So your should be, in fact, the ninth, it should be bigger than the second fourth.
Well, it's random.
Yeah, but
There's no guarantee.
it looks like the black and yellow two are progression, but not if you move on a ninth versus.
Yeah, it's not a. But the 14th gets you close to that.
Well, the ninth looks like it's in the 14th. The 14th looks like it's pretty low.
Yeah, but I think the point is it's sensitive. I think.
Yeah, I mean, the point is more sensitivity. I mean, we can't say this is right so much as they're more clustered, right? I mean, the main point here is that we would hope that things are sort of close together if they're being
Yeah,
perturbed.
if you look over around 25 foot level, right? 14 side looks like it's modest.
Yeah, I mean, this one, I don't know exactly what the 14th got slightly more than the 9th, but
That's 2,500 drop.
sure. I mean, so I'll say, I mean, this is true, but I don't know. From my understanding of the hypermassive neutron star phase, is it's very sort of sensitive to things and somewhat, I don't know that I want to say unpredictable, but it's not.
No, but this is actually a really nice test, right? Because if you stick in like a 14-digit perturbation, you don't set the seed, just run 10 of them.
Yeah.
Then you're gonna get this,
Yeah, you're going to get a spread. I would like to do that. I've not.
right, but it gives you, that would give you an effective confidence interval in your answers.
Yeah.
Which would be nice to have.
That's what I would like to see at some point, and I would like to. It would be nice if there was other codes that did a similar thing, so we could see what they look like.
You could make a Norman text.
We could, but yeah, I mean, this again, this is not a necessarily statistically significant set of data, but it is an interesting thing that we saw that we weren't actively looking for. That we were just wanting to see that our new code fell within sort of the perturbation range of the old code, and we instead saw that the old code was spread out way more. And it was something that we just sort of coincidentally saw and thought was an interesting result, not necessarily a statistically significant, but
10 minutes.
so yeah. And I'm gonna go ahead and move on, and then we can come back with more questions, just so I can show people sort of, I want to get to the very end of how to change their old bar piles. But so this is the same simulations. And I'm just sort of showing that the old one, you'll notice it has these like chips to the surface. So the right is the density, the left is the magnetic field strength. And you'll see that it has these like chips taken out of the surface, which, considering this is just orbiting, that's not very clean like one would expect. The new one has still got some bumps in it, but in our opinion, it's much closer to what one might think it should look like. And as we go into the merge, right, this still looks reasonably smooth, while those chips are just getting bigger and bigger as it's sort of distorting those weird parts on the surface. Now, once we get into the hypermassive neutron star, they still look roughly the same. Of course, the stuff out here is somewhat, it's mostly atmosphere still at this point, I think. So, you'll see some wisps, but I don't know how much you can really say in how significant the differences are out here for the evolution. Now, people have previously asked me things about how fast it runs or how much I've slowed it down. So I ended this. So the hybrid is in black, and what I'm doing is taking the time per hour that Cactus puts out and doing a ratio of the new code over the old code. And so the black down here is hybrid equation of state, and the blue line is just 0.97, just to give sort of a reference mark. And so it's slower by about 2.5%, which means that if you're doing a 30-day simulation, that's going to gain you about a day. Which, considering how much more sort of easier it is to change the code and manipulate the code, I think this is definitely a reasonable trade-off. The tabulated code, however, is faster by 20 to 60%. Now, I have some ideas where some of the speed up comes from. There are some places that loops over and tries different initial guesses. And the old code is doing some strange things in there, which would potentially cause you to guess the same thing multiple times. So this speed up is likely partially from there. These really noisy parts are because the two codes checkpointed at different iterations, because the x-axis is the iteration count. So these are just which code was checkpointing at that time. Yeah, and so the tabulated code seems to have improved significantly, and the hybrid isn't really that much slower, and it's pretty reasonable. So I'm just going to go over how you use the GRHayl thorn very quickly. So first of all, if you want to set the content routine, you just pass it the name of the routine you want from GRHayl. And then the backups, there's 0, 1, 2, because we have up to 3. And you just pass again the routine you want. So for the induction equation, there's we have the generalized Lorentz gauge. And so there's a Lorentz damping factor that you can set with this parameter. And then the size 6 threshold, what this is used, this is the default, which basically we follow. It's not going to ever trigger. But this sort of tries to predict whether you're inside the black hole. And if you are, it does some different things in some of the enforcing limits and other small things like that. These are setting, of course, so after content prim, we enforce limits on the primitives we computed. So the mins and maxes are used for that. And then if you have to reset to atmosphere, of course, the ATM variables are used for that. The mins and maxes don't have to be set. If you don't set them, they'll be turned off and they just won't apply limits at all. So now I'm going to look at the EOS. So this is sort of the simplest hybrid where you just have gamma equal to gamma thermal, and then you're setting K1, and then there's only one piece, so it's 1. And yeah, and this is just going to give you sort of the simplest hybrid setup for an evolution. Now, if you wanted to do a piecewise polytrope to match, say, SLY4, please ignore all the numbers you're about to see.
5 minutes.
But basically, you have to set all of these based on how many pieces there are in your polytrope. And you only have to set the first K, and it will automatically compute the rest. And then you just have to set all the gammas for each piece, and then you have to set the row values that tell it when to change pieces, which is why there's one less row in gammas. And then if you want to do tabulated, of course, then you're going to set the EOS type to tabulated instead of hybrid. And then generally you're going to want to evolve the temperature, and you can evolve entropy with hybrid or tabulated. If I just put it here just so you can see it. And then you're going to have to tell it where the table is for it to use. And then in addition to those row values you saw, you're also going to have to set ATM values for T and YE. And if you want, also mins and in tabulated, you're instead of it not setting it, the mins and maxes will be set to the table bounds if you don't set those. Now, the last thing is, if you have an old Illinois GRMHD program and you want to convert it, now there is backward compatibility, so it will still work. But if you want to use the new features and get rid of some of the old stuff that's in there, first of all, these two thorns aren't used anymore. If you're using the pure Hydro run from the ID converter thorn, just switch to using GRHayl because that's the pure Hydro code now. You don't have to use Illinois GRMHD for that. And then these are all just there's arrows in here of what the equivalent parameter is. I just include these so that they're a place you can see them eventually, and hopefully these recordings or slides will be somewhere and you can reference back to this. I don't think anyone wants to go through all these. But then there's also some deprecated parameters that we don't use anymore. Because like tau ATM, we can just compute for you instead of you setting it arbitrarily. And then similarly, these are just more parameters that get changed. And so, yeah, thanks. Questions?
Back to that presentation slide.
Yeah.
So,
You can go ahead and start asking.
that roundabout error perturbation of original code, that's something like a 25% different than 35 full fractional bad.
Yeah.
That seems pretty significant.
Yeah. Note though that I should note this is simulation time in cactus units, and
Yeah.
I don't know what that means in milliseconds off the top of my head.
I mean, that's still about 20-25% difference.
I mean, so, yeah, I mean, it's basically adding one whole extra oscillation on the star, right? Is what it's doing.
Yeah.
Because it basically just barely doesn't get high enough to collapse. And so it oscillates one more time, basically what's happening, right?
Which feels like a significant.
Yeah, I mean, I think it's definitely something, that seems concerning, but the question I would say is, I don't know that anyone has actually looked and seen how sensitive their codes actually are to this or not. I'm not aware if people have tried a similar test in other codes. I don't know if, anyone's done this with GRHayl, for example.
Yeah, I think everybody should do this.
I think it would be nice to see what other codes do, because, I mean, it looks bad, but without anyone else doing it, we have no way of knowing if other codes are just bad. Right, like that's something that I think we should look at is we should run other codes and try to perturb the initial data and see what happens, right? We should run with different, seeds and see what happens. I mean, maybe the old IllinoisGRMHD was just doing something bad, but maybe everyone's doing something bad. And I think it would be good to investigate. Because, if nobody tests it out and tries it, well, nobody will know.
Well, if you look at the old Illinois stuff,
Yeah.
the turf was good at 4,000, but they do when it's not good at 4,000. So
What do you mean not good?
Yeah, for the ninth perturbation.
I'm not sure what you mean by good.
Well, you get 4,000, the purple still oscillates kind of on the left. But on the right at 4,000, it's way off the chart.
I mean, sure, I mean, well, in theory, we would expect things to collapse at a similar time. Right?
Yeah, but it looks like one left did a better job for the ninth perturbation than one on the right.
I don't think that's clear, right, because he's got a single seed. Might be if he took a bunch of different seeds, then probably take the steer off.
Yeah,
Yeah, and the tough question is slide 40.
sure. Yeah,
Yeah, code less sensitive to small changes. Initially, the simulation is less sensitive. I don't know what the code less sensitive.
sorry,
is.
sorry, that was basically previewing this, that it
Yeah.
seems to be less sensitive to
Well,
the.
the simulation I agree is less sensitive. I don't know what the code.
That's what he means.
I mean, the simulation is driven by the code. So it's
Right.
to me, are the same state, but I don't.
And like, you do other scenarios,
Yeah.
you see like the same kind of significant difference, or is it?
I mean, the TOVs look, single TOV star looks basically the same.
As it would say, it's all those things.
They're right on top of each other. They're on top of each other if you change back the things we changed, right? So if even in a TOV star simulation, improving the metric derivatives, the fourth order actually causes the central density to be better preserved. You'll actually see if you make that change, then you have the right. So in a TOV star, right, in the ideal case, it would just be constant central density. But because of numerical errors, it starts oscillating and slowly losing central density rate. And the changing it from second order to fourth order actually causes you to lose noticeably less density. It clearly just raises it. So that is, we immediately see that in even TOV. If you look at the very start of the BNS, you also see the maximum density has a similar behavior. Now it's a bit disguised because there's another change we made because there's something in old IllinoisGRMHD that sort of it preserves the central density better, but for unphysical reasons. So we don't keep that, at least for now, because it basically lets the pressure go below the cold pressure for the hybrid equation of state, which doesn't make any sense at all, basically. And so we changed that to set the minimum to peak cold instead of 0.9 peak cold, which causes it to actually lose more of density over time, but it's before it was basically just tricking the code and preserving the density with it, like, there's not a clear argument anyone's made for why that was an acceptable choice in the code. But, I mean, if somebody convinces me that it should be that, then I can change it back. But thus far, it seems like that was merely an unphysical change that someone made because they said, oh, but the central density is better conserved, so why not? But it doesn't seem like that was actually a well-motivated choice based on what I've been. So when I was making GRHayl, I changed it that form. Yeah.
So for the fire specialization, are you using Stanford?
No, so the question is what initial data is I'm using. I'm not using Fluker for this. I'm using the Lorraine with the moon offloads.
But like ideally,
Yeah, Fuka should also work, I think. But back when I started doing all these, Fuka wasn't in yet.
nice.
I agree with DNS data. Also.
Yeah, I could also use DNS thing. What was your second question?
So if I were to do say like they just say with GRHayl and would you need another method that showed the last few slides?
Sorry, if you were going to implement what?
Like say I want to use the leakage speed.
Okay, so if you're going to use leakage, you don't need to change the conduit routines at all. So that all leakage does is adds extra terms to the right-hand sides of some of the variables. So basically, whenever you want to add neutrino leakage, there's if you look at the IllinoisGRMHD schedule .ccl, basically all there is there's one thing that basically makes sure that the hydro-based variables are set so that neutrino leakage ET can read them, because we use slightly different variables for the velocities, so we have to convert back to hydro-based before neutrino leakage runs. But then the leakage thorn just adds to the right-hand sides. So that's the only thing that it does. Yeah, John.
Does it not have to compute an optical depth somehow?
It computes that in the neutrino leakage thorn.
Okay, but is that not a global thing? You have to do it in all of these?
Yeah, that thorn does a lot of stuff by hand, I think. I honestly haven't really looked at that thorn much. That's Leo's sort of project. And all we sort of did was trade out the local functions, the GRHayl functions. So I can't really speak too much about what's going on the inside. But I do know he does a lot of like looping through things manually and computing things in there. Yeah. But that's all sort of outside of GRHayl. Like GRHayl just provides the core routines he needs, and then he's doing whatever he's doing based on how it runs. Any other questions? Yeah, Roland.
So you like we should individual modules make up GRHayl.
Yeah.
So one can basically mix and match those as performance. To which extent are these things sometimes a little bit hierarchical if I want to confirm
Okay. So Roland was asking about, I showed all the different modules in GRHayl, and basically how much is it hierarchical and how much can I actually mix and match. So all of them depend on having an equation of state of some sort, except for, I think the constant atmosphere doesn't probably, but basically everything does. In theory, if you wanted to write your own equation of state thing and replace all of the functions GRHayl expects to exist, you could, and then you wouldn't need to use GRHayl's EOS module, but that sounds like a lot of work to do, is to try to avoid using what we're giving you, but you could if you want to. But outside of the equation of state module, none of the others have any interconnects. So for example, the induction equation functions, some of them need the characteristic speeds, but all they know is you gave them a characteristic speed. They don't know how you got it. So as long as, yes, you can get it using the function that's in the flux source module, but you could also already have had it from your old code, and then you just give it to the GRHayl induction functions, and all it knows is you gave it a characteristic speed. It doesn't know where it came from. Are there any questions online? Yeah, Peter.
Okay, can you remind me again what this setup is? Yes.
Oh, this is a binary neutron star with hybrid equation of state. I don't remember the exact details.
We have a question.
Does that?
Can we simulate the accretion?
Well, if I want to compare this.
Oh, yeah.
Sort of-
Yeah, I can, if you want to talk to me, I don't have the part file on me, but we, maybe when I get back to Idaho, I could dig it up for you and we could try to come up with a set that maybe we want to try to pass around and see if people are willing to run it. See if what people can. What was the online question? Sorry.
It was like, go ahead.
No, I was ready.
Yeah, it was something about can you use this with an accretion disk? I couldn't see the whole thing.
Ron, can you, the question online, can you use simulate black hole, especially binary?
In theory, it should. I mean, so the RIT group I know uses or tries to use IllinoisGRMHD with circumbinary disks. I'm not really connected to that project at all, so I can't speak too much about how that's going. But it should work for that. The main question is where you want to get your initial data from, I think. But in terms of evolution, it should be fine. Anyone else?
All right, let's thank our speaker. That's our second day.
Yay. As people get back live.
The LIGO trip is tomorrow. Try to be ready to go at 12:45.